So I will talk about something we call structural sparsity in multiple measurements. And it is joint work with Johannes, you all know him, and also Sarah Krause-Solberg and Nada Sisuono. By the way, you can see my cursor, right? If I'm pointing on something. Okay. So I will first give you like a short introduction about this multiple measurements we're talking about the applications that Johannes mentioned. Then we will have a deeper look into this structural sparsity model. I will show the algorithm we developed, and in the end, some nice pictures, as I always say. So, so we already have seen the sparsity model in the last talk. Let's have a look again at the one for multiple measurements. So in this case, yk and xk here are vectors, so it's not coefficients, but vectors. And we say we have multiple measurements because we have for k equals 1 to L, we always have the system yk equals a of xk, so the same system matrix, but different measurements yk. And what we want to do now is we want to reconstruct the sparse solution xk. So we want to solve something like what's here, the minimum of xk in the sparsity norm and the zero norm, such that a times xk is equals yk. And of course, we could do this for each measurement, but this would be inefficient because in the multiple measurement case, you always have to consider that there are information or correlations between the measurements, and you want to take this into account. So what you're actually doing is you rewrite everything as a matrix system. A times the matrix X is equals our measurement matrix Y. So X now is just the matrix of all columns XK, and Y is just the matrix of all columns, all measurements YK. And when we look at the problem this way, then suddenly this matrix S X can have two properties. And the first one is still the sparsity, so the number of non-zero elements, which is the same property as in the single measurement case. So we still have some sparsity to measure here. But because we're looking at a matrix now, it can also have a structure, so the pattern of the non-zero elements. And because we have these two properties right now, we have to ask the question, is there some kind of norm or some measure we can take to measure both of these properties at once? So then we could minimize over this norm. And of course there are many examples for this. Like 3 examples I'm showing here on the top. There is the row sparsity, where you just look at the matrix and you count the non-zero rows. So in this example would be 3 rows, and you see there are much more than 3 non-zero elements because the complete row here is full of non-zero elements, but we only count the number of different rows. So what we're measuring is the sparsity plus the structure in ones. Another thing would be block sparsity, where you have different blocks that are non-zero and you just count the number of blocks. Or some models like joint sparsity, where each column has, like they have a joint sparse support that you see here, the 3 rows, and they have some sparse support on their own. Like each column also has some non-zero points that are not correlated to the others. So these are common models. But if you look now at the applications, so the applications we were dealing with here is seismic data. We've seen this in the last talk also, ultrasonic data, or we're also working on weather data. And if we, for example, look at this, can you see this when I'm zooming in? Because the pictures are quite small. Oh, okay. Then it's a bit better to see. So if we look at the seismic data here, Then you see there is some structure in there. We have like seismic waves on top of here, and we have some wave that's traveling through this image here, and here is another one. And there is some structure, but it is not the row sparsity. Let me go back. It's neither row sparse, not is it a block sparsity, and also not the joint sparsity at all. So there are many applications that have this sparsity plus structure, but the common structure models that you will find in the research, they don't fit these applications. So we were thinking about what more general kind of structure model can you design that would fit these applications and that is still possible to solve. And we will have a look at our model that we were introducing on the next slides. And for that, I want to start with introducing so-called elementary structures. And these are basically one-sparse structures that build up your sparsity model, if you want to say so. So let's say you have a sparse vector with only S non-zero elements. Then you can write this vector as a sum of S other vectors, and each of these other vectors is one sparse. So S sparse vector can be written as the sum of S one sparse vectors. That sounds easy. The same for matrices. Like if you have a S sparse matrix, so either row or block sparse, you can write it as the sum of S matrices, and each of this matrix is exactly one row sparse or one block sparse. And if you do it this way, then these one sparse elements here is what we call the elementary structures. And the interesting thing is, like we have seen it this way around now. You say the matrix is S row sparse, and then you write it as sum of elementary structures, but you can also do it the other way around. If you know what matrices are your elementary structures, then you can define the sparsity by this. And we will see this on the next slide. So let's say we have a set S. That's a set of all elementary structures. Then we can define a sparsity. So 0 here for the sparsity norm, and S because it depends on our set of elementary structures. And we can just say that X, the sparsity of X is the minimum amount of elements we need to write our matrix S as a sum of these elements, and the elements are all elementary structures. And by this way, just given the set of elementary structures, we can define the sparsity. So we can go this way around. And now the next question is, okay, what would be a good set for elementary structures? And we will see a problem on the next slides, because if you are too restrictive with your elementary structures, then they won't fit the application. But if you are too general, then it becomes harder and harder to solve the optimization problem in the end. So we need to find a balance in the middle. We need to find a good description for our elementary structures that is general enough to fit the applications, but restricted enough to that we still can handle it. If you look a bit in the literature, so this quite general model, if you just consider anything, any set, then you will find up the so-called atomic norms. There is some theory about this, but this is quite a general theory, and it's too complicated for the applications we have in mind. So we need to be more restrictive than those atomic norms that are considered there. Another interesting thing, if you just think of a finite set S, then the problem here becomes you want to cover some support of your X with a combination of elements of your finite set, and then somehow you will end up in a set covering problem. So this problem here is very, very related to the set covering problem. And here you can already see a difficulty. So if minimizing this is somehow related to the set covering problem. This means that even calculating this norm for one single element you have can already be NP hard. So you see that this definition here is quite general, and even just calculating the norm for one element can be NP hard. So minimizing the norm in the end can be much can be a very big problem. So yeah, as I said, we need to find a suitable choice of S. Let's first look at so our idea is based on the following. So if you look up the definition of structure, actually I did this for this talk. It says a structure is basically the arrangement or the relations between parts or elements of something complex. And if you want to translate this into something that is mathematics, then the key here is like the relation. So you need the relation between parts of something. So what we need is the relations between the non-zero elements of our matrix. So how can we put this in mathematical form? Therefore, let's say this x absolute value with the vector on top, this should be the vectorized version of our matrix, and so the absolute value is element-wise absolute value, just for notational reasons. And now we can look at the following quadratic form. This vectorized version transposed times the matrix C, we will later see what this matrix C is, times x. And if you write this out like this quadratic form, then you will see this is basically just a sum of all the relations between two of your elements in a vector in the matrix. So this gives us a relation between pairs of pixels in our matrix, you can say. And what we are doing is, okay, we say that if this relation we are calculating here is 0, then it is a good relation, so it's an elementary structure. And if this is non-zero, then there is one pair, at least one pair, that is somehow destroying our structure. So if this is non-zero, then we say it is not an elementary structure. So the matrix C is the coefficients I use here are double indexing, because you see we are this gives a relation between indices of our matrix X. So the coefficient C, ij, I prime, j prime is giving us the relation between the ij entry of our matrix and the I prime, j prime entry of our matrix. And we can either set it to 0 to say, okay, this pair is fine, this is allowed in our elementary structures, and this is basically a good relation or a good arrangement. Or we can set it to 1 and saying this is something bad, we don't want to have this pair in our elementary structures, so we set it to 1. And if we have this matrix, we can basically define all our elementary structures by this formula. And if we have the elementary structures, we can define our norm like as seen on the last slide. So that's its theory behind this. Now let's have a look at if this is like useful for something. And for this, maybe first two simple examples. We have seen the row sparsity before and the block sparsity before. So now we're trying to write the row sparsity and the block sparsity in form of this matrix. And this can basically be done very easily. So for row sparsity, we just set this coefficients to 0 whenever the row entry, the row index I and the row index I prime are the same, because then the elements, this pair of pixels we're considering here are in the same row. And this is exactly what we want for row sparsity. We want elements that are only in the same row. If they're in a different row, then we set it to 1. And now maybe I go back once more. Consider this one here, this quadratic form. And now the matrix X only has entries in the same row. That means each non-zero pair you can build is in the same row and will have a weight of 0 because it's a good arrangement. That means this all here will be 0. So the elementary structures of row sparsity that we form by this condition are all matrices that have exactly one non-zero row. So we see row sparsity works with this kind of model. What about block sparsity? Well, for block sparsity, we can say we look at the difference between the row indices if this is smaller than P, and we look at the difference between the column indices if this is smaller than Q. If both of these hold, then we can say these elements are in the same block and the block size is P times Q. If one of these doesn't hold, we set it to 1, and this means this pair has to be in 2 different blocks, so this structure can no longer be a elementary structure. So we see it covers some models before. The joint sparsity model we have seen before is not covered by it, so it is not a completely general model. There are still some restrictions to it, but it is more general, and we will see that it's quite good for the applications we had in mind later on. So on the next slides, I will show you how to construct a matrix just from the data you have, some construction idea that we gave in our research. But keep in mind, for the algorithm later on, we can use a very general matrix. The only thing we need for our algorithm is that the matrix, that the coefficients are all positive. You can choose a binary as here, but if you want to put some weight on some pairs, you can just use a general positive matrix. You can adapt it to your application as you like, with any kind of coefficients, like any combination of coefficients. The only thing you need to keep in mind, we already see here, like if, let's say our matrix X is a squared matrix n times n, then this matrix C will be n squared times n squared. So this will be a huge matrix, depending on your system. So what you need a way to deal with this matrix quite fast. And for our algorithm, that means we need a fast multiplication by this matrix. And for this, you can, for example, use that the matrix is binary, then the multiplication is actually not a multiplication, but addition. Or for the matrix we show in the end, you can also use that you can maybe write it in some Kronecker product form, then there are fast multiplication methods or something else. So this is the only restriction on the matrix, actually, that you need a fast multiplication for the algorithm. So the idea we were presenting, if you want to create this matrix C from the scratch, just from the data you have, is if you look at these measurements you have and at the atoms you have. So atoms, by atoms, I just mean the columns of your system matrix. So in some literature, you see the term like dictionary, that the system matrix is your dictionary with different dictionary entries. Sometimes it's referred to as atoms. It's just the columns of the system matrix. So basically the basis that you will use to make sparse linear combinations. And to understand the idea we have here, you can say if we have similar measurements, so the measurements that may look quite similar, then you also want to use similar atoms or similar columns of your matrix A to present those measurements. What do I mean by similar? Well, I mean, let's say we have two vectors, X and Y, and we take the inner product and normalize it by the norm of the vectors. Then this is something between 0 and 1. And if this is greater than a constant alpha that you may have chosen depending on the applications, then we say that this is similar. So for the next forms, we just assume that A and Y are normalized. So all your atoms, all your columns in A are normalized and all your measurements are normalized, because then we can just completely neglect these norms here on the to divide by these norms here and just have a look at the inner product. And then if we want to know which measurements are similar, you just look at your measurement matrix transformed times itself. And now look at everything that is greater or equal to the parameter alpha you've chosen. And this is a binary matrix that I call Y tilde. And I do something similar for your atoms. I look at all the inner correlations between your atoms, and everything that is smaller or equal than better. So all atoms that are not similar, I set these values to 1. So A tilde is exactly 1 for pairs of atoms that are not similar, and Y tilde is exactly 1 for measurements that are similar. And now I can just say the matrix C that now depends on these two parameters. We will see more about these parameters later on in the numerical section. I can write these as a Kronecker product of these two matrices. What does this make? So this makes C exactly non-zero. So it will exactly have a 1 at a position where the measurements were similar, but the atoms were not. So this means this matrix C penalizes if you choose different atoms for similar measurements. And by doing this, by defining this matrix C, we already have a sparsity norm that is adapted exactly to our measurements and to our measurement matrix that can be used here. So this was the first basic idea. Then you can improve this a bit. I will not tell everything in detail here, but maybe the idea behind this improvement is, if you look at the color coding of this matrix here, so the matrix C measures the correlations between the columns of your matrix X, and each block here stands for 1 column. So if you look at, for example, let's take this block where my pointer is in now. This gives you all the correlations between the first column of your matrix X that you want to reconstruct and the third column, like the first column from here and the third column from here. So, and then you see there are different types of combinations you can have. The blue one is all different columns. That means columns that belong to different measurements. The red boxes always compare the same column to itself, so correlation within one measurement. And the green is just the diagonal. And you can improve the matrix a bit by saying, first, on the diagonal, we only want to have zeros, because we don't want to compare one pixel in our reconstruction with itself. That's like not a valid pair. The second thing you can make is the C1 matrix is basically exactly the same as I've shown you before. This minus I here is just to remove all the entries from the diagonal blocks, from the red blocks here. And then the matrix C2, you see here, is the opposite of what we have seen before. So for the same measurement, we want to penalize if there are two atoms chosen that are similar to each other. By choosing it this way, we can remove this blurring effect that sometimes happens if you can't reconstruct the exact peak, but you will reconstruct something that looks like a Gaussian blur around this peak. And we can penalize this by setting C2 like this, and then penalizing similar atoms for the same measurement. Okay, so this was the idea how to choose our matrix C. This can basically fit for many applications. In the next, In the next chapter, I will show you more about the relaxation of the problem and the algorithm. And for this one, this chapter already holds again for any kind of matrix C that has positive entries, like positive or zero entries, not only for the special matrix I've shown you before. So the problem we would like to solve is this one here. So we want to minimize in our C0 norm. So this is the norm now defined by our matrix C, such that AX is equals Y. Or in the noisy case, we will see this later on, you will have plus the Frobenius norm here. So the problem is, we have seen before, calculating this norm can be NP hard, and solving this problem is definitely NP hard. So there's no way we can do this. We need to replace the norm itself. We need to replace the norm. Sorry, wait. I'm sorry. So we need to replace this norm here so we can handle this problem. And one thing we can show is if the norm, under some mild assumptions of the norm, so I've that it's basically saying that the columns of our matrix need to be one sparse if the element itself is also one sparse. In the publication, you will see later on, we can even relax this condition a bit more, but for this talk here, I think this is easier to handle. So if we have this mild assumption, then we can show that this term here, so instead of taking the norm, we only have the vector of 0 and 1s. This is basically saying we need this, we take the support of our matrix. And this term is bounded above by the norm and below by the norm. So this is behaving exactly like our norm, and we can just replace our norm by this kind of quadratic form. And this is what we're doing in the first relaxation step. So we see this here, instead of the norm, we take this quadratic form here. Then the second one is a quite common one that you also know from the single measurement case, where you replace the 0 norm by the 1 norm. What you're actually doing is you replace the support by the absolute value, and we're doing the same here. So we're going back to this absolute value vector of x, and we end up with this minimization problem. And then, as said before, in the noisy case, we take the Frobenius norm here of the residual instead of forcing the exact norm. So after this relaxation, we end up with this problem here, but we're still not done, because even this one is quite hard to handle. The problem here are the absolute values that make this problem so hard here. So we would like to get rid of the absolute values. One way would be if we know the signs of our solution. So if we know in which orthant the reconstruction X would be, then we could just remove the absolute values here and add the signs in our matrix C and A, and everything would be fine. Well, unfortunately, that cannot be done. Like, we can show that there are combinations where you cannot guess the orthant from an initial guess, but you can do a little trick. Instead of just considering the system matrix A, you can consider a system matrix A and minus A. So you combine basically the atoms and the negative atoms. So you add both signs here. And now it is possible to, in the sparse solution, to choose the atom that is positive or choose the atom that is negative. But that means we don't need to choose the sign in our solution at all. We don't need to choose the sign here. We can just take positive entries of our solution. So if we can solve this one here, you can see that our solution set that would just contain the positive and the negative entries of our original solution, and we can recover the original solution in this way. So by this trick, by lifting it to a higher dimension here, we got rid of the absolute values and we end up with this minimization problem. Now, it is important to notice this is still not convex. So we are still not at a convex optimization problem because this matrix C is not necessarily convex. This can be not necessarily positive definite, I mean. And you can try to lift this even more to a convex problem, but we tried this, and then in numerical experiments, you can see that basically the solutions you recover are no longer sparse. And this is because the non-convexity of this problem is actually what pushes the solution to the boundary, to the sparse solutions. So we somehow need to handle this problem here. But also this is non-convex. It can be handled by just looking at the following function. So f of z is just the function of our minimizer, and it is not convex, but it has some nice properties. First of all, it is bounded from below by 0, at least on the positive orthant where we are looking at, and it is coercive under very mild assumptions, and that already means, okay, there are some minimizers, and these minimizers are in a finite ball. So it would be possible to maybe find some minimizers of this one. The second nice thing is, this is actually a quite nice form. We can handle this analytically. So we can calculate the gradient of this one analytically. And this means we could maybe try to apply some gradient descent for this method. We need to be a bit careful. We need to update the gradient a bit in order not to leave this positive orthant here. But this is everything, and everything that can be handled quite nicely. Now, the next nice thing about this function is it is not convex, but it is quadratic. And this means once we have a descent direction and we look at this function just in the function of the step size, so f of tz, then because it's quadratic, it's either convex or concave. And that means if we think of the step size, we can just calculate the optimal step size. If it's convex, we can just minimize this term here. And if it's concave, then we know that the optimal step size will just bring us directly to the boundary. So although this is not non-convex, we can still handle it quite nicely. And here's the algorithm we're using. So we get this function. The first thing is you initialize it with the 0 solution. So we just start with x0 equals 0. And then we iterate just gradient descent. This means we calculate the gradient. Then we calculate the optimal step size. This here is just the step size we're choosing is just chosen in a way that the maximum is 1. This is just set by us because it proved quite nicely in the numerical experiments not to take a step size greater than 1. And then there are 2 other step sizes. The first one is the optimal one from the convex optimization. And the second one is the maximum step size such that we are still on the positive orthant. And we calculate all those, take the minimum of this one, and this is the step size we will choose. And then we just need to do an update step to update our solution. We can iterate this, and we will end in some local minimum. Okay. Let's have a look at some numerical results. So the first thing we did is experimenting on some toy examples with some structures that we built up. So the first one is here a structure with 2 diagonal lines. So maybe you need to look closely. So we have the main diagonal, and this one is also one diagonal line that just leaves on the right side and enters on the left side. Then the second structure is some lines that are slightly oscillating, and the third one is more close to the row sparsity model, where we have these 2 half lines here. For these, we did some convolution on these with a Gaussian kernel, and then added some noise. And we ended up, for example, for these oscillating lines, with these 3 examples on different noise levels. So you see a quite low noise level with 25 PSNR, then a medium one, 12.5, and a very high one with PSNR of only 2. And now we were just checking, like, how is the reconstruction quality of our algorithm compared to other methods. And here's the list of methods we took. So maybe to point some out, we have the E-star algorithm, that's iterative soft thresholding, and we have the G-E-star, that's a group version of it. So the iterative soft thresholding is a algorithm for a single measurement. So this is applied per column. The G-star is the same algorithm, but for multiple measurements, so this is applied per matrix. The same here, we have orthonormal matching pursuit and a multiple measurement version of orthonormal matching pursuit. And then we also have some sparse spatial learning algorithms. So different techniques designed for basically row sparsity or single measurement cases. And if you look at the reconstruction quality, it's quite clear, especially for the first 2 examples, that our algorithm is much better. But this is no surprise, because our algorithm was adapted for those kind of structures, whereas the other methods were not. But in the third case, where we have the row sparsity, even in this case, our algorithm proves to be better than the other techniques. So in the next cases, we were looking at some applications. Here I show you the one for ultrasonic data that we have seen in the beginning of the talk. So we have 2 ultrasonic measurements here, where you see some structures. And the normal model for these ultrasonic measurements is that it is some sparse structure convolved with an ultrasonic impulse. And the impulse we used, you see this one here in the first picture, the blue one for the left image and the red dotted one for the right image. These are not the exact impulses, so our system matrix is not the exact convolution matrix, but there is a bit of noise on it. But it's fine enough, it will do for the experiments here. And so you build the convolution matrix from these kernels, and then you use this convolution matrix as your matrix A, and this is your data Y, and you try to deconvolve with our technique. And what you obtain is these sparse reconstructions here. And for example, let me zoom in. Okay, I can see this here. The 2 pictures, then I'm skipping those. We're just showing that you can also choose these parameters alpha and beta that we have shown in the beginning directly from your data by just considering the physics behind these data. Then we also did this on the weather data, and here we said similar measurements are just measurements that are locally next to each other, so the sensors were next to each other, and they should have rainfall that is close in time. And by using this model, we can track a rain shower here moving from north to south, and here one moving from south to north in Germany. These would be the elementary structures, those kind of rain showers here. Okay, and I'm finished with this. We have a nice summary here that you can read, and here is the link to the